In this video lesson, we're going to cover how to draw a Lewis dot structure, and we're going to talk a little bit about what a Lewis dot structure is. Basically, I want you to think about this as a two-dimensional stick figure of the atom. Just like if we were to draw this and this, you would know those were stick figures, and you would probably assume this might be a boy and this might be a girl. If I drew this, you would assume this is maybe a cat or a dog. The point is, a stick figure just shows you in two dimensions the very basic features of that object, and that's what we're doing here with the Lewis dot structure. We just really want to show you when atoms come together and make a molecule, what's in the middle, and how are the other atoms arranged around that central atom. So you might want to jot down these quick notes first, and this is just kind of a little checklist. It won't make a lot of sense to you if you've never seen this lesson until we do some examples, but it'll give you something to think about. So first we're going to count our valence electrons to get our budget. It's an electron budget. And this budget's going to be pretty interesting because we have to use every single one of the electrons, no more, no less. It would be like me sending you to the mall with $100 and saying, you have to spend this to the penny. And I do want to remind you that when we count valence electrons, for this level chemistry, it's really easy. We just count over from left to right on the periodic table. So for example, aluminum would have 1, 2, 3. If the D block gets in your way, just skip it, because remember, the D block is a level behind. I'm going to assume anyone watching this video knows how to count valence electrons. Then we're going to draw our stick figure, and we're going to glue it together with single bonds. So our stick figure might look something like this, like if A is our central atom and X are the outer atoms, it might look like that. You know, if it has just two outer atoms, it might look like that. But this is what we're going to call our stick figure. And this single line that you see, this is a single bond. And it is made up of 2 electrons. I'm going to go into just a little more detail on that shortly. The next thing we're going to do is we're going to give all of our outer atoms 6 additional electrons. So for example, if we had something that looked like this, we're basically going to give these outer atoms 6 more electrons, and we're going to work our way around the molecule. You're going to see a lot of different examples of this. This is just one of many, but the reason we give each one 6 more is because we know that the atom's goal is to have a full octet, which is 8 valence electrons, and if we add 6 more, and you include the one that's being shared here, you have 2, 4, 6, 8, 2, 4, 6, 8. So when you hear me say give the outer atoms 6 more electrons, that's what we're talking about. All leftover electrons are going to go to the central atom. So for example, and just for simplicity, I'm going to draw another one with just 2 outer atoms. Once you've given all of the outer atoms their extra electrons, if there are any extra, there may not be. Sometimes there aren't leftovers, but if they do have leftovers, you're just going to pop them right there on the central atom, and you're going to learn that that plays a major role in the molecular shape of the atom in the next lesson that I'm going to teach. Once you've used all of your electrons, you'll hear me say hands off. That's when you've put that last electron down. You want to take your hands off. You want to look at what you've just drawn, and you want to ask yourself, is that central atom happy? You are going to know it's happy if it has access to 8 electrons. It could look like this. Even though all 4 of these bonds are shared, this central atom still has access to 2, 4, 6, 8 electrons. It may look like this. It's possible that maybe, well, it would look like this actually after sharing has taken place. But after sharing has taken place, this would actually make this happy. And again, you're assuming you've got all these little electrons around the outer atoms. I'm just giving you a quick look at this. Or it may be happy because it has a lone pair, which went ahead and satisfied that full octet, and then no sharing is going to have to take place. So you're going to see a lot of different versions, but when you're asking yourself if the central atom is happy, and you really wouldn't be looking at this yet, you would do that after that question, you're looking to see, does it have access to 8 electrons? There is one exception, and that's going to be boron. We're going to talk about that in a minute. And I did make a note here. If it's not happy, one of those outer atoms is going to have to share, and that's kind of the after that I had shown you right there. This is where we get double and triple bonds, and we're going to see that in more detail as we go through the examples. So a few good things to remember before we get to the point of actually drawing these structures. The central atom is happy with 8 electrons. Boron is the exception. It is happy with 6. I tell my students boron's on a diet. If the central atom's not happy, sharing has to happen. For example, if we had something that ended up, let's say we put all of our electrons down, and this particular one, every single electron was used, we said hands off. The next thing we would do is say, is the central atom happy? And the answer would be no, because there's only 2, 4, 6 electrons that this atom has access to. So what we would have to do is make one of these guys, and it's not going to matter which one in this case, we would take a pair of electrons from one of these and share it with the central atom. So sharing happens after we've put all of our electrons down and we have asked ourselves that $1 million question. Is the central atom happy? Boron, again, is the exception. If boron happens to be your central atom, it is actually going to be happy with just 6 electrons. Good to know, hydrogen never gets any extra electrons. If you'll remember, the hydrogen atom only has one shell of electrons, and that first shell can only hold 2 electrons. Therefore, you're never going to see hydrogen as a central atom. It's always going to be hanging on to that central atom. So if your central atom, we'll just use A again, it may have a hydrogen on each side, but we'll never add electrons in any way, shape, or form around hydrogen because it simply can't hold them. So hydrogen will never have electrons added to it. That's the only exception you'll worry about today. The central atom always gets the leftovers. We talked about that. These are called lone pairs. For example, if you had a molecule, you drew it, you put all your electrons down, and you still had 2 left over, they would go to the central atom. And then the last thing I want to mention that we're going to see in some of these examples is something called resonance. Resonance is a term that we use to describe a molecule that can be drawn in more than one way. For example, let's say that we drew this, and that's what we put all the electrons down, and that's what it looked like. Well, now we would ask ourselves, is the central atom happy? And the answer is no, because it's only got access to 2, 4, 6 electrons. What that means is one of these is going to have to share. Is it this one or this one? I don't know. You know, somebody might say, well, I'm going to make this one share. Someone else might say, and I'm just going to draw a quick, I'm going to make this one share. This molecule shows resonance, and what that means is that you can't really draw that molecule, all the different variations of it with just one model. It could be drawn 2 different ways. And again, we're going to go into more detail on all of this as we go through the examples. This is just giving you some things to think about. And lastly, for polyatomic ions, if you have a charge, you're going to have to take that into account when you are calculating your valence electrons, and in this case, you would add 2. So we went through that pretty quickly, and if you've never seen the lesson, that might be a little overwhelming. But now that we're going to do the examples, it's all going to make sense, and you'll be really surprised at how fast you catch on. So let's go ahead and jump in, and I'm really kind of working off the cuff today. I usually have little sheets made up with everything all worked out so I can move through them quickly, but this is going to be, this video is rough. I'm going to go through and actually do all these right along with you just like we were doing them from scratch. You may see a few mistakes just like anybody would make going through these. So the first one we're going to look at is Ci4. So we're going to count our valence electrons. That's the first step. So carbon has 1, 2, 3, 4 valence electrons, and I'm just going to jot that down. Iodine has, it's right here, iodine's got 1, 2, skip the D block, 3, 4, 5, 6, 7 valence electrons. Some of you just may know that because it's a halogen and you've already learned that in your chemistry class. So iodine has 7 valence electrons, but there are 4 iodines. So we're going to have to multiply that. So we're basically adding 4 plus 28, which is going to give me 32. So I have 32 valence electrons. I think it's important to write that down because that's your budget. You have to use all of those electrons to glue this thing together and then to finish it. So the first thing we're going to do is we're going to draw kind of the stick figure. Some people call this the skeletal model. Since there's only one carbon, it's pretty easy to see. Carbon's going to go in the middle, and we are going to evenly disperse the iodines around it. This is taking us into something called the VSEPR theory, VSEPR, valence, shell, electron pair repulsion. I'm going to talk about that in the next lesson. But basically, because all of these atoms are surrounded by electrons, they naturally repel each other. So you always want to spread them out evenly around the central atom because they need to be as far apart as possible while still being attached to that atom that is in the center. Think about a mom with 4 kids. If she's going to try to space them out as far as possible so they don't fight. And we're going to actually think about the central atom as the mama and these outer atoms as the babies. That might make it easier for some of you to catch on to this today. So we've drawn our stick figure, and now we're going to ask ourselves, how many electrons did I actually use gluing this thing together? Since each single bond is worth 2 electrons, we used 2, 4, 6, 8. We have used 8 electrons out of this budget gluing it together. Now the next step is we're going to add electrons to the outer atoms. And this is really simplifying things, but I tell my students, think of the central atom as mama. She has spent all day cooking a big old Sunday dinner. She sets her babies down at the table. That good Southern mama, what's she going to do? She's going to feed those babies first. And that's exactly what we're going to do here. We're going to start adding electrons to these babies, 6 apiece. So we've already used 2, 4, 6, 8. It does not matter where I start. I'm just going to start here. So we're going to pick up at counting at 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, hands off. Why hands off? Because I just used every single one of those 32 electrons. Once you take your hands off, you ask yourself the $1 million question, is mama happy? Because we all know if mama's not happy, nobody's happy. Is mama happy? Does she have access to 8 electrons? And the answer is yes. She has 2, 4, 6, 8. She is happy and we are finished. So that is the Lewis dot structure for Ci4. And while I'm thinking about it, I don't know if I mentioned, I know I didn't mention this earlier, but when we're looking at those single bonds, again, a single bond is 2 electrons, a double bond is going to be 4 electrons, and a triple bond is 6 electrons. And I'll go ahead and mention this while I'm thinking about it. Single bonds are going to be your longest and weakest bonds. So a single bond is 2 electrons. These are your longest and your weakest. A double bond is a little bit shorter. It's made up of 4 electrons, but it's a little bit stronger. Triple bond is shorter. It's made up of 6 electrons, but it's a lot stronger. So your single bonds are weak and long. Your triple bonds are short and strong. And you can think about a rubber band. If you've got one rubber band, you can probably pull it pretty far. You can really stretch it. But if you've got 2 rubber bands doubled up, if you use that same amount of force to pull, you're not going to pull them quite as far apart. If you triple up those rubber bands, you're not going to be able to pull them far apart at all. So single, double, triple goes weak to strong, long to short. So that's a good thing to know. You might want to jot that down if you didn't already know that. So now let's look at the next example, SES4. 3. So let's count our valence electrons first. Se has 1, 2, 3, 4, 5, 6 valence electrons. Sulfur also has 1, 2, 3, 4, 5, 6 valence electrons, but I have 3 of those, and 3 times 6 is 18. So 6 plus 18 is 24. So we have 24 valence electrons that we can use to build this molecule. So whatever you have one of is going to go in the middle. For most beginning chemistry students, that is typically what you're going to see. There'll be a few exceptions. Obviously, it gets more complicated than this, but we're keeping this real easy. So Se goes in the middle. Now, this time we have 3 sulfurs, so we're just going to kind of evenly distribute those. Don't get too caught up in exactly how you draw that. Just spread them out around the central atom. So we have counted our valence electrons, we've drawn the stick figure, now we're going to feed those babies. We're going to give these outer atoms 6 additional electrons. Now I have already used 2, 4, 6 electrons, so we're going to pick up counting at 7. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, hands off. I've used all 24 electrons. Now we ask ourselves, is the central atom happy? Is Mama happy? Does she have access to 8 electrons? And in this case, no, she does not. So let me give you a little scenario. Mama's cooked dinner. She set all her babies at the table. She has fed all of them, and Mama's not happy. She doesn't have enough food. If any of these little children have any sense, one of them better do what? They better step up and share, right? So does it matter who? No, it does not. We'll just make this one share. So to share, we're just going to take a pair of the electrons off and swing it between the two, and now we have a double bond. That's where double bonds come from. And something else, these are shorter, and doesn't that make sense? Because Mama's going to love this baby just a little more at the moment. She's going to pull it in for a hug. So those double bonds are actually going to be shorter bonds. Also worth noting, this shows resonance, because we could have drawn it like this because somebody else may have said, well, I'm going to make this one share. Someone else may have said, well, I'm going to make the other one share. And I didn't draw all the little electrons around them, but you get the picture. This shows resonance because it can be drawn 3 different ways. So good to note that right there. All right, let's look at the next one. BCl3. So let's count our valence electrons. Boron has 1, 2, 3 valence electrons. We already know chlorine has 7 because it's a halogen. 7 times 3 is 21, and 3 plus 21 is 24. We have 24 valence electrons. We already know boron's going to go in the middle. It's time to draw the stick figure. We're going to surround it by chlorines. We have 3 of them. And I just used 6 electrons gluing this together. It's time to feed the outer atoms. Let's feed the babies. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, hands off. I've used all 24 electrons. Is Mama happy? Be careful here. Normally, Mama would not be happy, but if you'll remember, boron is an exception, and it is happy with 6 electrons. So this is an exception. And this is one that we mentioned earlier, but it probably meant nothing to you then, but now you can see how that works. So always remember boron is an exception. I tell my students that Mama's on a diet. All right, let's look at another one. NH3, this happens to be ammonia. Nitrogen has 1, 2, 3, 4, 5 valence electrons. We know hydrogen has 1, but there are 3 of them, so 5 plus 3 is 8. 8 valence electrons. That does not look like much. So that might be concerning to some of you, like, how am I going to have enough to draw this structure? So let's just jump in and see what we do have to work with. We know that nitrogen's going to go in the center, surrounded by 3 hydrogens. And I have used 6 of my electrons gluing that together. Remember, a single bond is worth 2 electrons, and we have 3 here, so that's 6 electrons. Now, normally, the next thing I would do is I'd feed these outer atoms their electrons, but hydrogen is also an exception to the rule. Hydrogen only has 1 energy level of electrons, and that energy level can only hold 2 electrons. Hydrogen can't handle any more electrons. This is like a tiny baby, so it doesn't get anything extra. So I've used 2, 4, 6. Hydrogen can't have any. Who always gets the leftovers? Mama. 7, 8. We've put them all on the table. Hands off. Is the central atom happy? Yes, it is. It has 2, 4, 6, 8 electrons, and we are all good. This extra pair of electrons, these leftovers, this is called a lone pair. These are the leftovers. And leftovers always go on the central atom. So hopefully you're starting to see how this works. And now if I say this, it makes sense. Count your valence electrons, draw the stick figure, give your electrons to the outer atoms, throw leftovers on the central atom, ask yourself if it's happy. If it's not, make someone share. That kind of sums it up. But we're going to do just a few more examples to make sure you've got this concept. This will also be covered a little bit in the molecular geometry video. All right, PF3. So phosphorus has 1, 2, 3, 4, 5 valence electrons. Fluorine has 7. 7 times 3 is 21. 5 plus 21 is 26 valence electrons. So let's draw the stick figure. P goes in the middle, surrounded by fluorines, which are evenly distributed. I have used 2, 4, 6 electrons to glue this together. It's time to add electrons to the outer atoms. I'm going to start counting at 7. 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I've got leftovers. 25, 26, hands off. Right after hands off, ask yourself, is Mama happy? Is that central atom happy? And she is, because she's got 2, 4, 6, 8 electrons, and we're good, and we have a lone pair. It is really important that you put every electron on that table, take your hands off, and then ask the question, because if you ask the question before you do that, you may end up putting a double bond in the wrong place. So always put all the electrons down first, and then ask yourself if the central atom is happy. All right, now we've got nitrate. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. Oxygen has 6, 1, 2, 3, 4, 5, 6, but there are 3 of them. 6 times 3 is 18. Now, 18 plus 5 is 23. That looks a little odd because literally it's an odd number. We've been working with even numbers. But you have this special little thing here called a charge. And that -1 charge is like nitrates holding up a big sign that says, hey guys, pay attention, I have an extra electron. Because remember, electrons are negative. So we're going to have to add 1 more to that for that charge. So we actually have 24 valence electrons. So if there's a charge, adjust your electrons accordingly. If that would have been a positive charge, we would have subtracted electrons. Now we're ready to draw the atom. Nitrogen goes in the middle, surrounded by 3 oxygens. I have used 6 of my electrons gluing it together. Now it's time to give the oxygens their additional electrons. So I'm going to start counting at 7. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, hands off. I've used all 24. Now I ask myself, is the central atom happy? And the answer is no. Not happy because she only has access to 2, 4, 6 electrons. That means one of these need to share. Doesn't matter who. Let's make this one share this time. Take a pair of electrons off, swing it between the 2, and now Mama's happy. This also shows resonance. Because this could have been drawn 3 different ways. We could have put the double bond here, we could have put the double bond here, or we could have put the double bond here. All right, let's look at another one. We only have 2 more examples, and I think everybody's going to have this skill nailed down pretty well. So CS2, carbon has 1, 2, 3, 4 valence electrons. Sulfur has 1, 2, 3, 4, 5, 6 valence electrons. 6 times 2 is 12. 4 plus 12 is 16. We have 16 valence electrons. There's only 1 carbon and 2 sulfurs, so it makes sense. Carbon's going in the middle, sulfur is going on each side. I have used 4 electrons to glue this together. Now we're going to start giving these outer atoms their electrons, feeding the babies. So we've got 4. We're going to start at 5. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Hands off. Is Mama happy? She is absolutely not happy. Not only does she not have 8 electrons, she's only got 4. So she's very unhappy. So we're going to make 1 share. Doesn't matter which one. Now we ask ourselves again, is she happy now? And the answer is no. She's only got 2, 4, 6. Now here's the deal, and I mentioned this earlier. This one has already shared. And if this was your mom, you and your sibling, and you had already shared, and mom still wanted more, are you going to share again? Probably not. You're probably going to look at your sibling and say, you know what? I've already shared. It's your turn. And if the other one is capable of sharing, then it's going to have to take a turn. So this time we're going to take 1 off of this. Now Mama's happy. She has 2, 4, 6, 8. The only time both sides won't be able to share is in a situation like, I'm just going to make something up here. Let's say we have carbon in the middle and maybe a nitrogen and a hydrogen. And we filled everything in, and this is what we ended up with. Well, obviously, Mama's not happy. Hydrogen doesn't have anything to share, so nitrogen's actually going to have to share twice, and that's where you get a triple bond. So that's good to know. You know, all the examples we have seen, the siblings have been identical. All the outer atoms have been the same thing, but it doesn't have to be that way. We've just been doing very simple examples like you would see in a first level chemistry course. But sometimes the central atom has 2 different atoms. And in that case, if hydrogen is one of those, the other one's going to have to do a lot more sharing because hydrogen just simply does not have any extra electrons to share. Let's do 1 more, and you might even want to pause the video here. Hopefully you've been doing that, but if you haven't, maybe this is a good place to try it. Let's do this last one. You try it and then pick back up with me and we'll work through it. So silicone has 1, 2, 3, 4 valence electrons. Chlorine has 7. 7 times 2 is 14. So 4 plus 14 is 18 valence electrons. So we're going to put silicon in the middle and a chlorine on each side. We have used 4 valence electrons putting this together. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've got leftovers. Mama gets those. 17, 18. Is Mama happy? She's actually not. She's got 2, 4, 6. Even though she got leftovers, Mama's still hungry. Doesn't matter which one. This time we'll let this side share. And there you go. This also shows resonance. Because we could have written it like this, or we could have written it like this. It didn't really matter which side shared. And I do want to point out, speaking of resonance, this one does not show resonance. A lot of times, as soon as students see a double bond, they think, oh, that's resonance. This does not, because this is the only way we can draw this molecule. This is the only way we can draw this molecule. Resonance only happens when you have more than one way to draw the same molecule. So in summary, and hopefully I hope everybody's got this now. It's actually very easy. We're just going to make it super simple here. And I do think the mama and the babies make it really easy to think about. It's just a different way of looking at it. Definitely not super technical, but just an easy way to think about it. We count the valence electrons, we draw the stick figure, we feed the babies, we give leftovers to mama. When all the electrons are on the table, hands come off, and we ask ourselves the million-dollar question: is mama happy? If she's happy, we're good to go. If she's not happy, then sharing comes in, and that's where we get our double and triple bonds. So I hope this was helpful to you. I know I had a lot of students out when I taught this lesson, so I really felt like it needed to be covered on a video. It does go more in depth than this. There's more to it, but for any first level student, this should do it. I'm going to follow this with a second video called Molecular Geometry, and we're actually going to take these two-dimensional stick figures, and in our mind, we're going to pop them into three-dimensional figures, so you can really think about what that molecule looks like in 3 dimensions. So I hope this was helpful. If you have any questions, you can drop me a comment, and I'll make sure I look at that and address it.